the last class. These are different type of parameter like Y parameter or Z parameter or ABCD parameter that you have studied earlier. But these parameters, Y parameter, Z parameter, ABCD parameter, these are difficult to measure at high frequency. When we go to high frequency, all these parameters, Z parameter, Y parameter, ABCD parameter, these are based on measurement of voltage and current. Current and voltage measurement at high frequency is difficult. Although not impossible, but it is extremely difficult. Therefore, we have to resort to some other parameter which is easy to measure at high frequency. The measurement at high frequency, instead of voltage and current, if you multiply them, that is easy. So power, it is easy to measure power. So instead of voltage and current, we can use power to measure at high frequency. If we use power, then the parameters that we get are called scattering parameter, because it gets scattered at the object or at the port. So you impine an electromagnetic wave or a signal to a port, it will get scattered, the power will get scattered, and how much power is scattered out, how much power is going into the port, how much power is coming at other ports, those are giving us the S parameter or scattering parameter. Okay, this we discussed. Voltage and currents are not uniquely identified or defined at high frequency. Okay. Even if we find V and particularly I are extremely difficult to measure, this we discussed. Require open and short circuit conditions. Okay, this is also important that when we define the Y parameter and Z parameter, we require the current to be 0 or voltage to be 0 at one of the ports. That is extremely difficult to achieve. Scattering parameters are the best representation for multi-port network, which means more than one port. Now, to know or understand scattering parameters, you have to think in terms of incident and reflected waves or incident and reflected power on the transmission line or when the guide which is connected to a device. So look at this. This is a device, two-port device. This two-port device is connected on the two ports. We are connecting a transmission line. On the first port, port 1, the transmission line is Z01, characteristics impedance is Z01. For port 2, characteristics impedance is Z02. Between port 1 and port 2, there will be local port nets, so don't worry about that. What we will do is, at the end of the transmission line, we say the wave incident to the port 1 is A1. So wave incident to the transmission line connecting to the port 1 is A1. The wave coming out of the transmission line connected to port 1 is B1. Similarly, the wave going into port 2 or at the end of the transmission line is A2, and the wave coming out of the transmission line which is connected to port 2 is B2. The A coefficients A1 and A2, they are representing incident waves. B coefficients are representing the reflected waves which are coming out on each transmission line. Now you can see, using the transmission line theory, where I stands for the voltage, I stands for the transmission line number. So I can be 1, 2. If it is 2 port, I can be 1 or 2. So VI or voltage at the ZI is the position, So Vi at Zi is equal to Vi0 cross, which is the incoming voltage exponential minus gamma I Zi plus Vi0 minus, which is the reflected voltage into exponential gamma I Zi. So that we can write as Vi plus Vi minus. So on each transmission line, that is what we can write. Now think in terms of incident and reflected waves on the transmission line connected to the device. This we have seen. Now what will be I? Vi we have seen. What will be Ii? Current at port I. So current is Vi Zi by Z0I minus Vi minus Zi by Z0I. This is coming from your transmission line theory. We have found out what is the expression for V, what is the expression for I. So this is these are the equations that we get from the transmission line theory. Now what we will do is we will define a normalized voltage function. First we will define a normalized voltage function. So for the incoming wave function, the normalized voltage function Ai, that we define as Vi plus divided by root over of Z0I. So we normalize the voltage Vi with Z0I. So we write Aizi is equal to Vi plus divided by root over of Z0I. Similarly, Vi is equal to Vi minus divided by Z0I, which means we are normalizing the incoming voltage and outgoing voltage. The voltage that is coming towards the port and voltage that is going out of the port, they are normalized with respect to the characteristics impedance of the transmission line. Now, why we are doing in this? Why the wave functions A, B are defined like this? That there can be a question. The answer is the normalization makes power calculation easy. That is the first thing. Then, because of this normalization, you can get an unitary S matrix. So, unitary means a matrix whose inverse equals to the conjugate transpose of the matrix. So you take a matrix, take its conjugate transpose. If that is equal to the matrix, then that matrix is called unitary matrix. Now let us define the scattering parameters. Same two-port network, which will deal with two-port network, then we will extend it to three-port network or n-port network. So same thing. Assume the lines to be lossless, so Z0 is real. Power is equal to power at port 1, power at port I at Z is equal to 0. That will be, as you know, power is half V into I star. So use that real part of half V into I star. So use that, so this will be half real part of Vi plus 0 into Vi Ii plus star 0. That you can write as half Vi plus 0 mod square divided by Z0I. I is equal to 1 or 2. Similarly, we will recall now Ai is equal to Vi by root Z0. So using that, Pi plus is equal to half of Ai0 plus Ai0 square. Similarly, you can have Pi minus is equal to half of Bi0 square. So these are the two things. Now you can see that the parameters A and B, the wave parameters A and B, are actually connected to power. So we are dealing with power, as I told you earlier. We are dealing with power instead of voltage and current. We now deal with power through the parameters A and B. Through the wave parameters A and B, we are dealing with power. It is easy to measure the power. So let us start with one port network. This is a one-port network where to the far port a transmission line of section L1 is connected. So, and gamma L or the reflected coefficient, reflection coefficient, that is by definition Vi minus by Vi plus. So that you can write as Vi minus by Vi plus in the numerator and denominator, divide them by root over of Z01. So if you divide numerator and denominator by root over of Z01, then gamma L is equal to B1 by A1. So for a one port network, gamma L is equal to B1 by A1. So we say B1 is equal to S11 into A1. What is S11 in this case? S11 is gamma L. So for a one port network, S11 or the scattering parameter at the port 1 is the same as the reflection coefficient gamma L. So S11 is equal to gamma L. Now remember this. Try to recall this. This wave function, incoming wave function A or AI is equal to Vi by root over of Z01. Similarly, outgoing wave function Vi is equal to Vi by root over of Z0I. Similarly, now come to the two-port network. So we have seen one-port network. Now let us come to two-port network. In the two-port network, for linearity, this relation is to be satisfied. B1 should be equal to S11A1 plus S12A2. Similarly, B2 is equal to S21A1 plus S22A2. This is to satisfy the linearity. In matrix term, if you write it in matrix term, then the column matrix of B is equal to column matrix is equal to the square matrix S into column matrix of A. Square matrix S contains S11, S12, S21, S22. So you can write matrix B is equal to matrix S multiplied by matrix A. So this S matrix is called the scattering matrix. Now same thing for two-port network. From linearity we have seen B1 is equal to S11A1 plus S12A2. B2 is equal to S21A1 plus S22A2. S11, now from this we can say S11 is equal to B1 by A1 when A2 is equal to 0. From the first equation, look at the first equation, make A2 is equal to 0, that gives you S11 is equal to B1 by A1. Similarly, look at the first equation, make A1 is equal to 0, that gives you S12 is equal to B1 by A2. Now when A2 will be 0, A2 will be 0 when the port is matched, output port is matched. So A2 is equal to 0 means the output port is matched, nothing is getting reflected from output port. So A2 will be 0. Similarly, A1 is equal to 0 means input port is matched, nothing is reflected from, no power gets reflected from port 1. So A1 is equal to 0. Similarly, S21 will be B2 by A1 when A2 is equal to 0 when output port is matched, and S22 will be B2 by A2 when input port is matched. So here the condition is either the output port is matched or the input port is matched. Now by output port matched, what do you mean? Input reflection coefficient is matched with the output match output. Similarly, reverse transmission coefficient and input port are matched. Or the output is matched in the S21 case. Forward transmission coefficient, so with respect to output is matched. Similarly, output reflection coefficient with respect to input is matched. Now consider this two-port network. Continue with this. Uh, Suppose we have these two ports. In the port 2, the port 2 is matched and it is of semi-infinity length. So it continues up to semi-infinity. The transmission line connected to port 2 goes up to semi-infinity. In port 1, there is some reflection, there is incident and there is reflection. So we have S11, port 2 is matched, so S11 is V1 by A1 when A2 is equal to 0. S12 also you can represent in this manner. Pictorially you can represent S12 in this manner. A1 is equal to 0. Since A1 is equal to 0, in the port 1 you can assume that there is a matched port or a semi-infinite line connected to port 1. S21 again you can say the port 2 is matched or it is connected to a semi-infinite line. For S22 you can say that port 1 is matched or a semi-infinity line. Now come to port 3, 3-port network. So A1, A2 and A3, B1, B2 and B3. 3 ports are there. So A1, A2, A3, B1, B2, B3. This represents the 3-port network. For this, again, due to linearity, we will have B1 is equal to S11A1 plus S12A2 plus S13A3. B2 will be S21A1, S22A2 and S23A3. B3 is equal to S31A1 plus S23A2 plus S33A3. In matrix, you can write them as the proper manner. B1, B2, B3 is the column matrix. That will be the product of a square matrix of S11, S12, S13, S21, S22, S23, S31, S23, S31, S32, S33. That into a column matrix of A1, A2, A3. Now to illustrate, find out what is S11 here or S22 here, etc. Look at this. B2 is equal to S21 A1 plus S22 A2 plus S23 A3. That implies that S21, if you want to find out S21, you have to make A2 is equal to 0, A3 is equal to 0. So port 2 is to be matched, port 3 is to be matched. So under that condition, S21 will be equal to B2 by A1 when A2 and A3 both are matched. Similarly, this you can represent pictorially using this. A2 and A3 both are 0, which means both are matched. So to port 2 and port 3, transmission line connected transmission line is either a matched line, is terminated in a matched load, or is of semi-infinity extent. Okay. The same concept we can extend up to an N-port network. So we have seen port 1, 1-port network, 2-port network, 3-port network. Now you can extend it up to N-port network or a multi-port network. For a general multi-port network, Sij will be equal to Bi by Aj when Ak is equal to 0, K is not equal to J. So A1 will be, if it is 1, 1, I is equal to 1, J is equal to 1, then it will be A2 is equal to 0, A3 is equal to 0, A4 is equal to 0, etc. K is not equal to 0. All ports except the port J are semi-infinity in this case, or they are matched at true. Now in this case, suppose you send an incident wave on port J and measure the outgoing wave on port I. When all lines except the line connected to port J are semi-infinity or terminated in matched load, and thus there is an incident wave only on port I, there is no incident wave on other ports. On other ports only there is outgoing wave, no incident wave. Now, why we normalize? So some comment on the normalization. If all lines entering the network, they have the same characteristics impedance, then Sij is equal to Vi by Aj, that is equal to Vi minus by Vj plus. Because of normalization, Vi by root of Vi by root over of Zi, that will be this root over of Zi in the numerator and denominator will cancel out. So that will give us Vi minus by Vj plus. When Vk plus is equal to 0, and k is not equal to j. So there is no difference between normalized and unnormalized scattering parameters. So this is one important point. There is no difference between normalized and unnormalized scattering parameters. They are same. In general, if you have different characteristics parameters or characteristics impedance, then unnormalized scattering parameter Sij is equivalent to Vi by Vj, Vi minus by Vj plus. Whereas normalized scattering parameter Sij is equal to Bi by Aj. The denominators in the or the division by characteristics impedance, the characteristics impedance are not equal, therefore Vi by Aj is not equal to Vi by Vj. So that is why normalized scattering parameter is different from unnormalized scattering parameter. Now let us look at the properties of the S parameter, which is important, which you need to know. If you have a reciprocal network, which means the network which contain only reciprocal material, the S matrix is symmetric. That is the first property. S matrix is symmetric for reciprocal network, which means Sij is equal to Sji if I is not equal to j. So if Sij is equal to Sji, then the matrix will be S matrix will be equal to its transpose matrix. So S12 is equal to S21, S31 is equal to S13, etc. Therefore, when you take the transpose of matrix, it will be same as the matrix. Now, if you have lossless network, the S matrix will be unitary. Unitary matrix means the transpose of the matrix multiplied by the complex conjugate of the matrix will be same as the complex conjugate of the matrix multiplied by the transpose of the matrix will be same as the identity matrix or unit matrix. That implies that S transpose is equal to S complex conjugate inverse, or that you can also say that S inverse complex conjugate. So S transpose is S inverse complex conjugate. That is what is called a unitary matrix. In the unitary matrix, the complex conjugate of the transpose matrix is the inverse of the matrix. There is an alternate notation for this, which is S dagger or SH, which is equal to S transpose complex conjugate. This S dagger or S inverse, these are called the Hermitian conjugate or Hermitian transpose matrix. Now, let us consider the first part of the unitary equation, which is S transpose into S complex conjugate is unit matrix. Then for n-port network, take I, j element. So input at I, output at j, so that type of element you take. Then from the first equation, S transpose into S complex conjugate is equal to U. From that equation, we can, if you expand that equation, that will also give us summation over k is equal to 1 to n, n being the number of ports. So summation over K is equal to 1 to n Sik transpose into Skz complex, that is by matrix multiplication. So that you can write as summation over K is equal to 1 to n Ski, Ik transpose is Ski, so Ski into Skj transpose, that is equal to unit matrix. Unit matrix means delta Ij. All elements except the diagonal element are 0. So when I is equal to j, those will be 1, others will be 0. So that is why delta Ij, delta is called the Kronecker delta. Delta Ij is equal to 1 if I is equal to j. Delta Ij is equal to 0 if I is not equal to j. So from that we can say summation over K is equal to 1 to n Ski into Skj star is equal to delta Ij. Now what is the physical interpretation of this? Physical interpretation is simple. The inner product is Ski into Skj star. So that is A is 0 unless I is equal to j. Now let us look at other properties of the S matrix. Let us consider a 3-port network. S is equal to S11, S12, S13, S21, S22, S23, S31, S32, S33. That is the S matrix. Now if you look at this, the rows, they always form a orthogonal shape. Each row forms an orthogonal shape. This follows from the starting with the second part of the unitary equation. If you look at the unitary equation, Sj into Sj star is equal to Si into Sj star is equal to delta Ij. So everything is 0 unless I is equal to j. When I is equal to j, this is 1. So which means S11 plus S12 plus S13 is equal to 1. The rows form orthogonal shape in this. Physical interpretation is all the power outgoing on ports is equal to all the power incident on ports. So whatever is incoming, that will go out unless it is lossy. We are not assuming a lossy network. So unless it is lossy, power coming in will go out. Now consider the properties of a 3-port network. All 3-port networks cannot be reciprocal, lossless and matched at all 3 ports. Any 3-port network. Consider any 3-port network, it cannot have this property. The 3-port network at a time cannot be reciprocal, lossless and matched at all ports. Now we will prove this statement, this property. This proof is by contradiction. Suppose there is a 3-port network which is reciprocal and lossless and matched at all the 3 ports. Suppose that is there. So S is equal to S11, S12, S13, S21, S22, S23, S31, S32, S33. When all ports are matched, then S11 will be 0, S22 will be 0, S33 will be 0. So the diagonal elements will be 0. Now if it is a reciprocal network, then S12 will be S21, S13 will be S31 and S23 will be S32. So using that, the S matrix now becomes 0, S12, S13, S12, 9. Why S12? Because S21 is equal to S12. So S12, 0, S23, then S13. Why S13? Because S31 is equal to S13 because of due to reciprocity. Similarly, S32 is equal to S23 due to reciprocity. So last row is S13, S23, 0. Now here S12 is not equal to 0, S13 is not equal to 0. Now use this property. The row, the sum of the squares of the row is equal to 1. So S12 square plus S13 square is equal to 1. S12 square plus S23 square is equal to 1 for the reciprocal network, lossless reciprocal network. Matched reciprocal network. Now, what does this mean? This means that S13 is equal to S23. So S13 is equal to S23. That indicates that will be possible only if S13 is equal to 0, which contradicts the condition that we saw in the past. We gave S13 is not equal to 0, S12 is not equal to 0. So this contradicts that condition. So it is not consistent with the solution for S matrix that we have obtained. So this S matrix is invalid. Now, dropping this condition that S is reciprocal, let us drop that condition. Then S matrix becomes 0, S12, S13, S21, 0, S23, S31, S32, 0. Now use again this property. Summation k is equal to 1 to n ski skj star is equal to delta ij. So if I use that property, then S31, S32 star is equal to 0, S12, S13 star is equal to 0, and S23 to S21 star is equal to 0. Then the other property is S21 square plus S31 square is equal to 1. S12 square plus S32 square is equal to 1. S13 square plus S23 square is equal to 1. Look at these two equations. This second equation will be satisfied only if S12 is equal to S23 is equal to S31 is equal to 0. Otherwise, this will not be satisfied. Other condition will be S21 will be equal to S32 will be equal to S13 will be equal to 1. So these two conditions, and S13 is equal to S32 is equal to S21 is equal to 0. Or S31 is equal to S23 is equal to S12 is equal to 1. Either this condition or the second condition, in this case, this will be satisfied. Now suppose it satisfies the condition S12 is equal to S23 is equal to S31 is equal to 0, and S21 absolute is equal to S32 absolute is equal to S13 absolute is equal to 0. This condition, if it is satisfied, this results in a circulator providing a clockwise circulation. With proper choice of phase, we can put these values. If you put these values in the S matrix, S is equal to 0, 0, 1, 1, 0, 0, 0, 1, 0. Similarly, if the second condition is satisfied, S13 is equal to S32 is equal to S21 is equal to 0, S31 is equal to S23 is equal to S12 is equal to 0. This results in a circulator providing anti-clockwise or counterclockwise circulation with proper choice of phase by using phase matching. S is equal to 0, 1, 0, 0, 0, 1, 1, 0, 0. So this is about the properties of S matrix. I hope you could have understood up to this. Then we will have a note on Z0. The S parameters depend on Z0. The Z and Y parameters do not depend on Z0 or the characteristic impedance of the line connecting to the network. So the device is a section of a transmission line. We can always model the device as a section of a transmission line with S11 is equal to 0 when Z0 is equal to ZS. ZS being the characteristic impedance of the transmission line. So S11 will be 0 when Z0 is equal to ZS. And S11 is not equal to 0 when Z0 is not equal to ZS, which is the general case. So in general, characteristics impedance of the transmission line will not be equal to the characteristics impedance of the equivalent transmission line for the device or for the network to which the transmission line is connected. So this is a small node on Z0. Then there is something called signal flow graph, which you might have studied in the Pojar book. This is a way of graphically representing the S parameter. Look at this: B1 is equal to S11A1 plus S12A2. Consider a two-port network. B2 is equal to S21A1 plus S22A2. Now this network that we have seen is equivalent to the network shown in blue. The wave amplitudes are represented as nodes in the signal flow graph. So A1, B1, A2, B2, these are all nodes. From the nodes, the power is going. So from node 1, it goes to the junction. At the junction, it gets divided as to, if it goes to the to port 2, it is S21. So it goes to port 2 from 1. Then if it is coming back, then it is S11. So then it comes back to S1. It comes back to B1. Similarly for B2 or A2. So this way you represent this. The rule is the value at each node is the sum of values coming into the node from the various other nodes. Using this, you can always draw a signal flow graph. So with this, I think we will stop. If you have free class, if you are free, we will consider some examples later. After lunch, we can consider some examples that you have to tell me. For the time being, we will stop. If you have doubts on